Yeah, just share my screen real quick. It's a pretty small group here, but that means y'all get to be able to ask more questions, which is nice. All right. Can people see my screen? Perfect. Thank you, Divya. So, welcome to the STAA57 review seminar. Um, it's presented by Valdy, one of our course reps, and myself, the co-president for AMACSS. It's actually my first review seminar, so it should be an exciting one. Just note that we're not TAs for this course. We're simply here to help your understanding with the world of data science, and note that this does not count as material to be brought into the exam. And quick spoilers that final exam solutions will be covered. So just a quick itinerary of what we're going to go over. So for the first hour, we're going to review the course material and understanding of the course material. And then for the second hour, we'll be going through the sample finder together. Are you ready? All right. So for week one, um, we're going to zip through kind of the first half of it because y'all have already done this for the midterm, and most of the content would probably be on the later half, but let's go through for loops, while loops, and if statements. So here are some of the problems that were brought up from the interactive practice. So how to solve factorial 10 with a for loop. So you iterate through 1 to 10 and multiplying by each of the indices, and then you print it out. And then the second problem here is just alternating between the plus and minus signs up to 100. So if the mod is 0, then we subtract it. If it isn't, then we add it. And for this third one here, we find a maximum value of n for which 1 plus 2 plus 3, etc., plus n is less than 4,000. So for this one, we first set two variables. So a being the total number that we're adding to, and b being the constant that we're adding one every single time, and we're running this through a while loop, and we're making sure that a plus b is less than 4,000, so that we can get this maximum value here. But be careful, because when you do this, y'all have probably seen from trying this practice out, when you iterate through this, you will run it one extra time, because the while loop will still satisfy the condition of being less than 4,000 when you add your n. So that's why we print b minus 1 here for printing what our n is. Are there any questions with week one? We'll move on to week two. So here's a quick intro to tidyverse. These are going to be very useful functions for just kind of seeing what the data is like. So reading CSV, of course, you can use glimpse to see the first column. You could also use head, which will show you the variables in the first row. So it's like column-wise, row-wise. And you can create vectors with C. You can use sequence, so SEQ, instead of with for loops to create a sequence. So for those problems earlier in the interactive practice, you can use sequence as well for them. There's a class hierarchy, which I'll explain as like logical is weaker than integer, integer is weaker than double, and doubles are weaker than character. So let's say you have a vector with strings, doubles, integers, and logical statements, so true false statements, then the class of that vector would actually be character, because it overrides all these other ones. So yeah, hopefully that kind of makes sense. And then, yeah, you can index vectors in many, many ways, using Boolean operators, using other vectors. So let's say x is our vector, and we have C1, 3, then that's the first and third index. You can also use negative indices and true or false statements as well. So yeah, there's a lot more to this in the R file, so feel free to look at that for more info. Some summary stats on the side here. You have mean, sum, variance, standard deviation, min, max, median range, quantile, and IQR. And there's a couple questions actually about the quantile and IQR, so those are good functions to keep note of. And here were some of the practice problems that were given in the R code. So this was using the MT cars dataset. And basically we want to create a summary of the average miles per gallon. And so we use the summarize function here, which is also very important. So we'll move on to week 3, which is about data wrangling and ggplots. Any questions about week 2 before we move on? Feel free to speak up or type in the chat. If all good, then yeah, for data wrangling and ggplot, we have a lot of functions here to kind of manipulate the data. So the first part was kind of like the data exploration. Now we're getting into manipulation. So you can use select for columns, group by for condensing rows, case when, that's okay. I got a question. How does class hierarchy apply to this course? What examples might we see in it? So there was an example in the R code for week 2 specifically. Let me see if I can pull it up. Oh, there's so much on the screen. Okay. Maybe it wasn't in here actually, but I did see it in the slides somewhere, I believe, where you could see which class there is for a certain vector. This probably isn't that important. An example where it could come up is like you have a vector that is mixed with like strings and integers. And if you did like is numeric, then that would actually give you false. So this is just for like exploring what's in your data set. So let's say you have that mix of strings and integers. If you type in is numeric and it gives you false, then you might think, oh, that's a bit weird. There might be a string in there that we might need to get rid of before we proceed with analysis. So like in some cases with data cleaning, it's helpful. Hopefully that answers that question. Yeah, for week 3, these are again the interactive practice questions where we have the petals and you select the petal length and the petal width using starts with. So starts with is a good string identification function where you can type out the string and it basically rejects it to find whatever string pops up for this data set. So yeah, and then part B here is creating a new column for the PCA of the petals. So yeah, C and D were also important to get, first of all, the aggregate, the mean of each species, and for D, it was using those quantiles that I mentioned before to see what's in these petal PCAs. So using this, the end result that we get is a scatter plot. So running this code gives us a scatter plot between the length and the width. So the width being on the x-axis, sorry, the width being on the y-axis, the length being on the x-axis, with the colors being the levels of the petal. And of course using geopoint for the scatter plot. Hopefully that kind of makes sense. I don't know if I'm going too fast here, but just rushing through this first half, because I'm sure y'all have been through this before. Here we have the Dippler cheat sheet. I like to use this a lot to kind of help me with what functions I need. Um, Same with the ggplot one. It gives you like geom histogram, geom bar. Um, so yeah, this is just something that I like to use, and could be useful for yourselves as well in terms of like finding what you need. Um, and yeah, we'll move on to week 4, where I believe Valdy will be going over the material. Wait, sorry, let me look at chat. Okay, there we go.
Okay, so should I share my screen?
Yeah, sure,
Or
you can share your screen.
so in week 4, you dive into a
Mhm.
ggplot still, and I think some of the things mentioned before by Yihoi was mentioned in this slide. So basically, in this week, they focus more on about the plots and how to use ggplot to make different types of graphs. So the general way of doing this is you just first start with the ggplot, and in the in the arguments or the parameter you put in as the data, which is the data set you want to use, and use AES brackets, and you put these 3 variables usually generally as the variable, like the x equals the first one, then the y equals the second one. And if you want to put some color, like line colors, then you put color here as the group indicator of your variables. So yeah, so this color and the fill later on, which is a little bit different. So color is for the colors of the lines, and if there's a shape, then if you want to color it, then you use fill. So for example, like in the bar graph, if you want to have color for the edges, then you use color. But then if you want it to actually be filled in, then you use the fill. So the different types of plots are scatter plots, so there'll be a lot of dots on the plot. So you use GM point. Then histograms is just something similar to like a bar graph. And density plots just plot the density. So you just remember the different functions. And there's also box plot, line, and smooth line. So I think the most common one you probably use is the scatter, histogram, line, and smooth line. So just remember that these are options that you have. So if the question asks about like plotting something, just use the one that you think the question is trying to ask, because they'll always have a graph and you try to recreate it. So just see which one is suitable. Then there are certain things that you should remember that for your labels. So if you have a numerical labels, so like it's 0, 1, 2, 3, 4, then generally R will treat it as, or like the ggplot will treat it as like a number. So that means that if it's 0, 1, 2, 3, 4, it'll be different shades. So it's like gradients. But if you don't want it as gradients and they're like this, like the numbers represent different labels, then you need to put use factor, like use factor before the variable you put inside. So just put factor inside. So this will make it, instead of numbers, they'll be treated as individual labels. And if you want to have many different graphs plotted at the same time for different data, so for example, I have like a data, a column with 3 different labels. So maybe like label A, label B, and label C. Then if I use facet wrap and I put that column inside, then I add that, then it will create the plots, but then it'll be divided into like 3 plots, one for label A, one for label B, and one for label C. So that's what facet wrap does. Then if you want to modify the labels, then you just use X labs and Y labs, and you can put equal to something as the parameter. That's for week 4. Oh yeah, there's also pivot wider and pivot longer. So these are I think he always tests this, at least in my experience, he tested it. So you just need to first know what the differences between pivot wider and pivot longer is. So pivot longer just makes your data longer. suggested by the name. So that's generally when you have like a very narrow data set where there's like a fewer columns, but there's so many rows. And if you want to make some of the rows turn into columns, you use pivot longer. So basically, it will convert the data from having a lot of rows, it becomes longer, the data. So you just have more columns. So maybe it's better if I annotate. So if you have a data set and one of the data columns are maybe like favorite color, then um, if instead of having it as one column and you can have it as like red, blue, green, like red, blue, green, it will rename it. It'll make these like all the red as one. Like, it'll make it red as a column, the blue as another column, and green as another column. So it'll make your data much longer. So the arguments is always this, the ones that it's always the same thing, where you put the data, and then the calls will be the column you want to transform. So it'll be like the favorite color, and it'll be the names. You need to give the certain names for the columns that you want, and the values will be from this column basically. So it just this is the syntax you should remember, and generally, so they'll ask you either to make it from um to use pivot longer or pivot wider. So just remember which one you have to use, and the syntax is this. Like just I think it's also in your lecture notes, so you just need to remember the syntax. And pivot wider is just the opposite. So you have very wide data, so many columns, and you wanted to make it into one column, like a lot of column, like some of the columns you combine into one column, and this will make you have more rows. So more rows basically means like from before, if you have like red, blue, green, it becomes to one column, and that makes it one column. Wait, sorry, I think I confused the two. Pivot longer does the one I just explained was pivot wider, and pivot longer is the one from three columns. It becomes one column basically. Yeah, so more rows, sorry. So I confused it. So what I explained before from having one column to many columns is pivot wider. And if you want to have it many columns into one column of color, for example, I have now color where there's like red, blue, green, that will be pivot wider. Yeah, so that's pivot longer and pivot wider. So if I confuse you guys, so basically um, pivot longer makes you have more rows, and pivot wider makes you have more columns. So I would just suggest be familiar with how to use the code. You don't have to really remember the code, but for this exam, just remember where to find it and how to use it. Then the next weeks, they have some important concepts about distribution and CLT. So first of all, let's talk about what is a distribution. So basically, it explains how a random variable is the probability of a random variable being a specific value. So for example, it's like if you roll two dices, then a random variable will be like maybe you can define it as the sum of the two dices. Then basically the specific value would be the sum of two dices, right? But we don't know what the two like there's many values that the two dices can be like, if you add them up. So if you have a probability for each sum, then that will be like the distribution. So the probability of the two dices adding up to two, that will have a probability. Then the probability of the two dices being three, that will be another probability, and so on. Then you generally describe this by a PDF. So a PDF is just a function that tells you, oh, if my specific value is this, what is the probability? That's as if that's generally for yeah, so that's for that. Then for the um, exponential distribution, then if you want to do that, you need to use PEXP to get the probability. This is like the PDF function, and the rate is 0.2, and the value of that you're trying to find is 1. But if you want to find the quartile of it being 0.5, you do this function. So exp is just to indicate that it's the exponential distribution, and p is the probability, and q is the quantile. And for exponential, there's two things. No, there's only one parameter you have to write, which is a rate. So it's 0.2. That's like the one I give. But if the question asks for a different rate, then you need to just change this. For normal, it'll be the same thing where there's p and the norm, and also q and norm. But in this case, we need to have two parameters. So we need to put a mean and a standard deviation. And similarly, there will be something for Bernoulli and binomial. So you just have to use the function. I forgot which one it was, but I think it's in your lecture slides. So just understand how to use these functions and that wire distributions. And basically what CLT is the central limit theorem. And it just states that no matter like what type of distribution your data is coming from, so if it's an exponential, normal, and Bernoulli, if I have the sampling distribution, so sampling distribution is I take a sample and I get the mean. And I keep doing this until I get a distribution. It will always approximate to be a normal distribution as long as in each sample, I have a enough sample, a number of data in one sample. So again, a sampling distribution is like once it's like you keep taking samples. So one sample is like maybe I take 30 data, then I take the mean, that'll be my first data point. Then maybe the second time I take another 30 and another 30. I keep doing that and keep calculating mean, and I plot it as a graph. Then that'll be the sampling distribution. So remember that as it grows bigger, it doesn't mean that we take more samples, but instead it means that in one sample that we take, we have more samples. Because we have to take a lot of samples of like 30. So for example, we have a sample size of 30. So we need to increase it larger and larger for it to approximate a normal distribution, basically. Then week 6 talks about sampling, so the sample distribution again, and estimation and bootstrapping. So if you keep taking samples, then the plot x bar is the mean, will be a distribution of a normal distribution. And by CLT again, like before, as we increase the sample size of each sample, then x bar will approach mu, which is the population mean, and sigma squared over n, which is the population variance over the number of samples you're taking per sample size. So this is just what CLT says. This is more on the technical side, but I think what you should know from the graph is that if I take a larger sample size here, you can see that my graph shrinks and it becomes more concentrated in the middle. Like it becomes more accurate and it's closer to the population mean. And you can also see like because it's divided by n that the variance gets smaller, so it shrinks closer. So it gets shrinks closer to the center and it gets closer to the population mean. So it's probably going to be around here. So now we're talking about estimation, and there's two types of estimation. So there's the point estimation and the interval estimation. So calculating a single point, such as calculating the mean of 10. So for example, point estimation is like you calculate the mean. So it means that it's just like getting a single value. So that's why it's called a point. So it's like you get 10 values and you make it into the mean. That's just 1 point you get. So that's why it's called point estimation. While interval estimation is you find a lower bound and upper bound, which is likely to contain the true parameter. And if you're confused why we're calling it true parameters, because we don't actually know the true parameter of the population because we only have a sample. So if we have a lower bound and upper bound, which we create by the sample, we can like kind of contain which contains the true parameter or like describing the true parameter. So generally you're doing this by doing a confidence interval. So and this basically confidence interval just tells you that like in this case it's a 95% confidence interval for the mean. So we know that okay, you can think of it as the like there's a 95% chance of it being inside. That's like the very easy way of thinking it, but it's not exactly correct. So what a 95% confidence interval is like if you keep taking samples and of the same size and you make 95% confidence intervals, then 95% of your confidence interval will actually have your true parameter. But if you want to like think of it intuitively, it's just like how you can understand a confidence interval, like how it can be used. It's just basically inside this 95% area of the graph, there's most likely going to be the parameter. And if you want to think about the code is pretty simple for finding confidence interval. So a set seed just basically just make sure that your randomness is set. So when I call R norm basically just generates data, 60,000 of them, with a mean from a normal distribution of mean 160 and standard deviation of 10. And this will create a vector of length 60,000 of different values. And because I set seed, if I keep running this code, it'll be the same. And then if I do S sample the population of size 30, that means that I'll get a sample of size 30 from the population you just created. Then if you want to do a confidence interval, you just need to do a t-test. And in the t-test, they give it to you here, the confidence interval. So that means my lower bound is 156 and my upper bound is 163. But then this is for a 95% confidence interval. So if you want it to be a different percentage, you just have to mention in the t-test. So on the right side, you can see that my confidence interval, I set it to 0.9. And when I do the test, it's going to be a 90% confidence interval. Then another concept is about a prop test. So previously it's about finding the mean. So it's like, where does the mean lie? We're trying to find a lower bound, upper bound for the mean. But in this case, it's a proportion. So it's like a proportion of something being something basically. So instead of, because it's proportion, it's going to be a little bit differently. So in the beginning, it's still the same where we generate random data. But now we make it so that it's a Bernoulli variable because for a proportion, you just need to count how many are above something divided by the total population. So in this case, we just define it as if you're above 182, then you'll be counted as 1. If not, you'll be 0. Then we take a 30 sample again, and in this case, we have to do prop.test to create a 95% confidence interval. And the x will be the sum of the s. So that will basically be the number of people greater than 182.88. And the length is just the total data set because it'll be 30. So you can think of it as a fraction of the people, like this parameters are like a fraction of the people above 182.88. And again, if you want a 90% confidence interval for the proportion, it's something similar, but the confidence interval is 0.9. You just need to set it. And so just always take note in the question what they're asking. And the final concept is about bootstrapping. So bootstrapping is a statistical method used to estimate the distribution of bootstrapping is a statistical method used to estimate the distribution of a sample statistics. So such as a mean, variance, or regression coefficients by resampling the data with replacement. So generally what it does is if you don't have because we don't have the whole population generally, but we have a sample. So what it does is it kind of creates a population from the sample. So it just keeps on sampling a lot of values. And so we can see here, this is how you create a confidence interval using bootstrapping. So this is the real population. So if we have a sample here of size 10, then we want to do the bootstrapping. So the bootstrapping here, basically, you resample from the sample that you already have, and you just set the size of the resample you want, and replacement is true. So remember, you can always you can resample the sample that you already took from. So it's like you're sampling from a sample, and the replacement is true. So you can always retake the same sample again. So then you just return the mean because we're asking for the mean. So and then after that, we just replicate it 1,000 times. Oh, sorry, 100,000 times. And so that means that we're getting the mean of 100,000 bootstrap samples. And lastly, we just create the quantile. So this is the CI, the confidence interval. So we want the confidence interval from like we want a 95% confidence interval, so we want the 2.5 and the 97.5. So the values of those two. So you just remember the code. So just you have to understand how to use the code for bootstrapping. So again, I'll repeat it. So you get a sample, and the bootstrap function just basically takes the sample from the sample that you already have, and just make sure that your replacement is true, and you do whatever you want to the sample. Like if you want to calculate the variance, you return variance of the boot. If you want the mean, you do mean, and you just replicate it a lot of times, and you can get the quantiles for the confidence intervals. So if you have any questions about my part, then I will answer now. I'll just message me and I'll answer it. But if there's no questions, I think I see some questions and I'll just answer in chat. Okay, so one question was about the pivot. Oh, so first question was about the set seed. So yeah, set seed was you can put any constant you want and it just tells you. So because if I keep running this code, um, it will always be different because there's randomness from the R norm. But if I put set seed, it makes it so that I can put different set seeds and it'll always be the same. So like if I put set seed 1, it won't be the same as set seed 111, but if I keep running set seed 111 by itself, it'll always be the same value. Then the other question was about pivot longer again. Sorry about the confusion before. So pivot wider makes it so that you're instead of having one column with a lot of values of rows, so like you'll have many columns. And pivot longer does the opposite. So it goes from many columns to one column with many rows, basically. So yeah, sorry about the confusion. I think that's it for this part. So if you still have any questions, just ask me. If not, we can move on.
All right, then I'll pick it up from week 7. So week 7 goes over hypothesis testing and p-values. So with hypothesis testing, you typically have a topic or a subject called mu. And this can be like anything from average population, average income, some sort of average, or some sort of guess, because this is your initial baseline and you want to see if the data supports this guess or not. But usually we want to try to reject the null hypothesis. And to do so, we have an alternative hypothesis called HA. And this differs from our null. This can be like HA is not the null, HA is greater than null, HA is less than the null. HA could also be the difference between two different metrics. And yeah, we can never really prove a hypothesis. We either reject it or we fail to reject the null hypothesis. So this chart here is the 2x2 table for, I think, what Shams calls the confusion matrix. So when you have H naught is true and you fail to reject H naught, then the outcome is correct. But if you have H naught is true, but you reject H naught, then this is what's called a type 1 error or a false positive. And when H alternative is false and you fail to reject HO, then you get type 2 error. And oh shoot, sorry, this should be actually true and true. Sorry, I'll edit that afterwards. But when this is H alternative is true, H alternative is true. So when H naught is true and H alternative is true for these, and because H alternative true, we fail to reject H naught, then we get an error because that's a false negative. And same for this one, it should be HA is true, and we reject the H naught. Um, that is correct. So the false negative is when it's true, but we fail to reject the H naught here because that supports the H naught evidence. And where p-value plays into this is that it's the probability of the outcome being more extreme than the observed data under our null hypothesis assumption. So we have our null hypothesis, and let's say we see a distribution of our observed outcomes. If we have let's set our level of significance to like 0.05, then if it's on that tail end of 0.05, then it's more extreme than our observed data. So an example I like to use to illustrate this is flipping a coin 10 times and you get 9 heads. That's quite a low probability of happening. So our p-value, the probability of having this happen is quite small. It's like 0.000 something. And so we reject that the null hypothesis that our coin is fair. For week 8 here, we're comparing two populations. So there's quite a lot of tests. So I've made this table here to kind of list out what tests could pop up and what they're used for. So the one sample t-test, we use t.tests with x and mu being a value. So we're comparing basically the sample mean with the population mean and seeing if it's different from each of them. For the two sample t-test, we compare two independent samples. And one thing to note here is that we assume equal variance. So we're assuming both of these samples have equal variances to use this two sample t-test. But let's say we don't have that assumption. Let's say the question says that there might not be equal variances, then it's safer to use the Welch t-test. And to run the Welch t-test, all you have to do is set the variance dot equals false with the t-test function. And so this compares the means of the two independent samples with unequal variances. And basically that means that we don't care about the unequal variance here. And we also go over the paired t-tests, which compares the means from the paired samples. So like for example, like before and after, where you're trying to compare the means of the pair. So you might have something like mu x minus mu y. And so that's when you'd run the paired t-test. For the f-test, you'd have equal variances for this. And basically, this is for testing if two samples have equal variances. So we went from the means to the variances now. And it's basically like replicating the two sample t-test, but for variances. And then we get into the two sample test for the equality of proportions, which Valdy went over earlier, where you're comparing proportions instead of means or variances. And some important metrics to note here is that you want to have the number of successes and the total count as well to run the test, so that you get the proportion of successes. What I mean by successes is like, for if you have a null where you have like an equal, like a fair coin, for example, then your successes could be like heads, number of heads. For the permutation test, this one's quite lengthy. It's seen a lot in the last few pages of week 8, and this kind of goes over your non-normal distributions, non-equal variance, and it's basically creating your own test statistic out of the sampling distributions by swapping these labels over and over. And you're comparing that to your observed difference. So you have like mean x minus mean y, for example, and you're constantly swapping these labels. So I'll show you the code here. So a good way to think about it is like one, calculate the initial test statistic, two, construct the test statistic distribution, and then calculate the p-value. So here we have our observed difference, mean x minus mean y, and then we're replicating it a bunch of times, and we're trying to approximate our test statistic here. So we have a sample of our x and y values, and we're basically taking the mean of that minus the mean of um, the ones that come after it. So, and then for our p-value, we take the mean of the absolute value of our repetitions and seeing if it's greater than the absolute value of our observed difference. So our initial difference that's brought up here. So basically, like this chunk of code, it's shown in week 8. If you know how to pull this up and implement it, then you should be good for permutation tests. Hopefully that makes sense. For week 9 here, so here we go over the different coefficients to see how accurate a model is. We go over the Pearson correlation coefficient. So depends how close the points are to the line. So like if you have a line like this, if a bunch of points that are a bit far, then that'd be a low Pearson correlation coefficient. Whereas if you have a lot that are closer, then that'd be a stronger correlation. You can also have negative correlations as well. So you can have a line that goes down to indicate the negative correlation. But what matters is the strength of this correlation. So whether it's positive or negative, how close the points are to the line determines its strength. Then there's least squares, which minimizes the sum of square differences. So you'd have your square differences like x minus xi, and you take the sum of that. Which translates a little bit into mean squared error. But yeah, we go into regression, and basically for regression, you assume a normal distribution for when x is equal to some x, and your y is your data set basically. And you have b1 being the starting constant when x is 0, and b2 is your slope for whenever your x goes up or down. So if you move 1 unit to one unit up or down on your x-axis, then that change your overall y value, which is reflected in the distribution. And some useful functions to help with this is summary. So summary would give you your coefficients. So it'd give you b1, it'd give you b2, and it'll also give you a t-test of it. And another one is confidence interval. So confident to get a 95% confidence interval by default. So yeah. And a way you can calculate how accurate this regression line is through the r-squared coefficient. And so is how much of y is explained by a variation in x. So if x goes up and down, how much of that explains how much changes in y. And this goes from 0 to 1, and 1 is typically the best. 1 is the best, but typically like you'd see values that are like between 0.5 to like 0.7, and anything above 0.7 is usually pretty strong. So in your exam, if it wants you to interpret your r-squared coefficient, then you can write about that. Yeah, for your mean squared error, it's just 1 over n, sum of your yi's and y predicted squares. And then for bootstrapping, we went over this earlier, but basically to have a confidence interval, you can either use Confident or you can use bootstrapping to get a wider population to get a more accurate confidence interval. So you'd use the replicate function and the quantile function at the end to get your interval. Right. How do I clear everything? There we go. And then here are some like concepts that delve a little bit into the ML side. So correlation versus causation. Um, this is like logic. So you see a change in X, and whether it causes a change in Y is often a false statement because you don't have the proper context to say that it causes this change. Whereas you can say a change in X correlates with a strong change in Y. So whenever you have a good R squared, you have a good Pearson correlation coefficient, you have a good residual sum of squares score, mean square error score, then you can say that it has a strong correlation. But yeah, don't say that it causes a change. Um, Overfitting and underfitting. So overfitting is like when you have a bunch of points here and you have a model that's highly dimensional. So basically it follows the points a little bit too closely. Sorry, that's a bad example, but and the problem with overfitting here is that once you get out of your training data set, so once you get out of this, then it's gonna it's not gonna know what to track afterwards. Basically, it's gonna be super highly dimensional, and you don't know if that's the general trend that these points are following. Um, and underfitting is the exact opposite problem. So let's say you have a bunch of points like this, and let's say it looks kind of parabolic, but you just have like a straight line going through it, then this isn't accurately uh, modeling how these points are. So think about like a low dimension uh, plane compared to your high dimensional vectors. For cross-validation, you basically have a data set where you split it into training and testing. So let's say you have like 75% train and 25% test. Well, the split that you have, let's say you choose this as the first three um, quarters as your training set, then you're left with this as your test set. But then for cross-validation, we mix it up. So then we take these three as their training, and then this as the test. And then we take these three as training, and then this as the test. And it goes over and over until you cover all your bases. Polynomial and spline regression, I don't think this will pop up too much. So I won't talk too much about it. But basically, you're combining a bunch of different regression lines together so that you get a model that can have both like high dimensions and low dimensions. So you can have a model like this and it goes like that, for example. And yeah, let me clear the drawings. Week 10, so oh, sorry, I see a question in chat. Oh, gradient descent. Yes. Yeah, and yeah, what Divi said is correct. Optimizing. But for week 10, we get into logistic regression, and the concept behind this is we have a Bernoulli distribution. Either it happens or it doesn't. And we want to categorize our data to this distribution, basically. So like, is it happening or is it not happening? And for a model that can predict these kind of decisions, we can use odds ratios. So p over 1 over p, 1 minus p is odds. That's not to be confused with the actual odds ratio, which is taking two samples and having the odds of the first sample being divided by the odds of the second sample. So that is odds ratio. And using this, we get into logistic regression, where we use the log of the odds or log of the odds ratio for our dependent variables so that we can classify them as, is it happening or is it not happening? Is it 0 or is it 1? And a key note here is that if you see log odds ratio being 0, then we don't see a change in odds. So there's no effect on the independent variable, our y variable. Sorry, our independent variables, the x variables on the y variables, so the dependent variables. So basically it's saying like the odds are the same, so there's no difference between them. Or there's no like significant relationship. Yeah, this is not part of the exam, but you can also get like log likelihoods for maximum likelihood estimation, for estimating your parameters, for our parameter values. So just a quick side note. But then we get into bootstrapping again for the confidence intervals. So the same concept as before, you use the replicate function and then use the quantile function. But one thing that's different is that we use the GLM function here for logistic regression, and we extract the beta 2 coefficient. So in your boot function, you use GLM and extract beta 2. And then we get into the receiver operating curve. So the ROC curve is basically a curve between the false positives versus the true positives. So from that 2x2 confusion matrix that we went over earlier, it's basically saying like how much of our data set is giving us true positives versus false positives. And the more true positives we have, we say that's a stronger model because we're not getting like a bunch of false positives from this. So the closer it is to 1, the better the classification is. And how we calculate that is using the area under this curve, so the AUC value. So you take this area underneath and then give you your score for how well this logistic regression model classifies. Hopefully that kind of makes sense in terms of like logistic regression and how these false positives and true positives relate. Like if you have in your test data set, you predicted something was 0, but it was actually 1, then that's like a false positive. So for week 10, there was also decision trees. So here we get into some libraries that'll help you with plotting trees. So the rpart libraries need for the rpart function to make your decision trees, as well as the fancy rpart plot to make like the fancy nodes and how they split off into different classes. So you use predict to predict your class labels. So you have here a data set and you mutate it to add a new column, and you can predict your class labels, so using type class. And yeah, like I mentioned earlier, you can create the confusion matrix as well to get your true negatives, false positive, false negatives, and true positives using table. And then this was from the data set from the week 10 exercise, but it was basically like which survived and which didn't. And so your actual versus your predicted. And then to get your accuracy, you'd basically take the diagonal, so the sum of the correct predictions. So you take your your false negatives and your true positives, and you take that sum to get your accuracy over your total predictions. So it's like these two here over the sum of all these counts. Um, and yeah, you can set multiple predictors or maximum depth for more intricate classifications, but I don't think that'll. I feel like that'd be too complicated for the exam. Um, Week 11, we get into bagging and random forest. Just realized we're a bit low on time, so I'll try to run through this pretty quick. The difference between decision trees and random forest is that random forest is basically a lot of decision trees because decision trees is just one split, whereas random forest we have a lot of them. We have a bunch of subsets of nodes. And bagging is a strategy to create trees through bootstrapping. So here we get less variability, but we're still using the same model for each node. We're still using the same predictors. So we still get quite a lot of variability within the prediction. But random forest is a bit better because we use a subset of the features. So let's say we have a data set called like crabs, and you have like crab height, width, length. Then some of the features, oh, sorry, some of the decision trees within the random forest would only use like length and width, or like height and like claw size, for example. So it wouldn't use every single variable. And you can also use decision trees as a regression. So basically to do this, you calculate the MSE for the observed Ys and the average Ys. So taking the average of each cluster and then comparing that to the observed. And yeah, the lower MSE, the better. Week 12, we go over missing value imputation. So this one is like when you have NA values, when you have missing values, there's a few options that we have here using the Nanier package. So option 1, 2 are not recommended. It's just like removing rows, removing variables. Option 3, 4, and 5 are more commonly used. So getting the mean of the data and replacing the missing values with the mean. You can also use the median as well. For things like age, it's more appropriate because you don't see decimal values with age usually. And then for option 5, you'd basically take the regression to predict your missing values. So using LM to impute your missing values. There's also a package that can automatically do this process, simputation. So yeah, I think that should be everything. And yeah, coalesce to skip over non-NA values. So if you don't want to use this imputation package and you want to do it manually, then you basically have this line of code here where um, you use coalesce instead of predicting. So yeah, I'm just gonna pause there for a minute to see if anyone had any questions, but that was kind of a brief overview of the course material. Hopefully that helped out with clearing up some concepts. And then we'll jump into the sample final. Yeah, some key concepts here to bring for the specific final is interpreting p-values, selecting which test to use for the comparison of two samples. There's also like some tidyverse stuff, so with your mutates, your selects, and everything, summarize. Then it wants you to create a logistic regression model, a linear regression model, as well as decision trees and random forest models. So if no one has any questions, we can go straight into the practice final. So here we have question 1, where we want to recreate the following table. And immediately what we want to do is we want to ingest the data. So we want to see what is this admission data here. And so what we can do is we can read CSV and we can run head or glimpse. I personally like to use head, and we can see that, okay, we have an admit column, a GRE column, GPA column, and a rank column, as well as the indices with each one. And immediately here we can see that there's way more columns there are than in our original data set. So there's one more, right? And so we know off the bat to use pivot wider at some point in our code. Another key feature that pivot wider has is you'd see a lot of these zeros and ones, like these categories that come at the end. And usually that indicates there's been some grouping that's been split up into columns so that it can be ingested that way instead of row-wise. So here we have mean GPA and the variance of the GPA. So we also know that we need summarize at some point to get the summary of the mean and the variance. And to do that, we'd probably need to group by the GPA and group by the status of the admission. So here, admit 0 is you were not admitted, admit 1 is you were admitted. And so if we want to find out the mean GPA for those who weren't admitted, we'd probably need to group by those people that didn't get admitted and had GPA. So that's exactly what the first line of code does. Can anyone take a guess who hasn't looked at the sample final yet? Of what the first line of code might be to group together the admission status and the GPA? Well, if no one has any guesses, then basically we use group by. So use group by, admit, and rank. And so here we want to get this grouping of GPAs and the admission values. So we use group by there, and then we use summarize to get a summary of the mean and the variances. And so off the bat, I'll show you what this first part kind of looks like. So this is what we have after using group by and summarize. So we have our mean GPA, we have our rank, and we have our admit. But now we want to use pivot wider so that our admit values, zeros and ones, they get appended to our mean GPA values so that we reduce the number of rows that we have. So from what Valdy mentioned in the format of pivot wider, this ID calls is not needed, but we do need names from. So we're taking the names from admit, and we're taking the values from the mean GPA and the variance of the GPA, and then we're appending it basically to the names of these. So the names prefix, here we have admit underscore, and this prefix comes after the values. So you're taking the values from mean GPA and variance GPA. So you're taking mean GPA and then prefixing with admit, and then we're having the values that come from admit here at the end. So the zeros and ones. And that's how we get this table here. Professor Shams does use this knit_r function to get a cleaner looking graph. So it's up to you how you want to use it. Here, I just went over kind of a pivot longer example. So let's say you have this data set. You're given this data set and you want to pivot it longer. So you want to turn it back into this basically. Then what we can do is we can use pivot longer. So you take the columns, the GRE and the GPA, you take the names to whatever metric and the values to some value. Oh, sorry, that one was this example, sorry. This one was just making the original data set longer. So this one was just making this original admission.csv data set longer. So here, if we want to, basically make the GRE and the GPA into rows instead of its own category in a column. So we see here that it's named to metric, GRE, and GPA, and the value for each corresponding one. So instead of having this being a category on its own as a column, we have it in a column called metric with both of them. And here's what I meant earlier by turning it back into the original mean GPA, variance GPA from after we pivot longed it. So to go from this to this, we'd make it pivot longer by unselecting the rank, so everything but the rank, names to dot values, basically for separating the columns into mean and variance, and then admit for splitting the string into the zeros and ones that we have. So you can take a better look at that, but for time's sake, I'll just move on here. For 1B, it's recreating the side-by-side scatter plot graphs. So it wants you to recreate the GPA versus GRE score, where we have both admitted and not admitted for the GRE versus the GPA. And we can see here it's a scatter plot because of all the different points on this plot, as well as a smooth line with a confidence interval around it. So what we do here is we want to split it into ones that are admitted and not admitted. And here's where we use the case when function, splitting admit equals 0 or admit equals 1. And so we do that right here. So case when admit equals 0, then it goes to not admitted, and otherwise it goes into admitted. And from the format earlier, we use the data set that we have. We put in GRE as our X values, Y as our GPA as our Y values, and then we use geom_point for creating the scatter plot. One thing to note here is we use adds factor because rank is a categorical value. It's not a continuous value, so we use adds factor to convert rank into these numerical categories. Stat smooth is the smoothing line that we see. And here we're basing it off the admit values. So that's where we put admit into stat smooth function. Yeah, you can read into local polynomial regression fitting, but it's not that important for this exam. And then here, facet wrap, basically it splits it into your two graphs. So you split it into the admit 0 and admit 1. And then here is all your titles for your x-axis, y-axis, and your main title. I'll pass it off to Valdy for question 2.
Okay, so I'll take off where he left off. So okay, so here's my screen. So I'll start with question 2. So let's see the question first. So the question 2, maybe I should share. Question 2, deals with data from the admissions data, and it says that, okay, let me show you the question first. Okay, so here, so the question two talks about you have admissions data and you want to compare the level of the GPA between the students who did and did not get into the graduate program. So basically there'll be a column with did and one of them that did not make it. So the first question asks us to test whether the variance of a GPA is higher for students who got admitted in the comparison to the students who did not get admitted. And this use a level of significance of 0.1 to interpret the p-value associated with your test. So basically, if you take down the question, what you're gonna have to do is the first part just tells you to do a variance test to check if it's higher. And then once we get the variance test, we get the p-value, and we need to compare it with the significance level. That's basically how we do the first part. So if you see the code is here. So if you see the code, then the first part we're doing the variance test based on admit, so the people who got in, vs the people who did not get in. So this is how you extract the data of the GPA. So remember, we're comparing the GPA of the people who get in and the people's GPA who did not get in. So to get the data of the people who got in, we of the GPA. So if we want the GPA, we first do the data, the D, and we put the dollar sign with the GPA. So that extracts the column of the data with the GPA. And because we have this condition, it only extracts the rows of the GPA where admit equals 1. So we get the GPA of the people who got into the graduate program. And the same thing for the people who did not get in, but instead we do it 0. And generally, if we don't put alternative equals greater, it means that we'll have a two-tailed variance test. But so generally, if the question says to test whether the people is higher, you have to make sure your alternative is greater. If but then if it's not greater but it's not equal, like says, imagine the question was test whether the variance of the GPA is not equal, then you just remove this part and you make it the default. But in this case, because we're talking about higher, then we have to put alternative as higher. So once you run this, oh, wait. Once you run it, you'll get a p-value. So remember, in this case, where it tells us to interpret the p-value. So our p-value is this value here, 0.5889. And because the p-value is greater than the significance level, then what you just have to mention is we fail to reject the null hypothesis of equal variance. So this is like a statement that you just have to kind of memorize, that if it's greater than 0.1, you just fail to reject the null hypothesis. But if it's less than, then you just reject the null hypothesis. So that's how you do question 2A. And for 2B, it says here, so it's something similar again. Assuming the population variances to be equal, we want to test the equality of the population means. So it says you use average for students who got admitted is higher than the average for students who did not get admitted as your null hypothesis, and 0.1 level of significance. Interpret the p-value with your test. So we want to test if the equality of the means. So we use a t-test, and the t-test will test the mean. And again, you use the data, the same data again. So the first part will be the ones who got the GPA of the people who got admitted, and the second part will be the GPA of the people who did not get admitted. And again, it says here, use average of the students who got admitted is higher. So again, higher means that our alternative has to be greater than, so greater. Then once you run this code, you will get our p-value as this value here, just remember, just extract the p-value, don't care about the remaining parts, because they only ask you about the p-value. And if the p-value, since the p-value is less than 0.1, in this case, we reject the null of equal means. So basically, the null hypothesis stated that the means were equal, so we just rejected the null hypothesis. And the question C deals with the checking the equality of two means of GPA between the two groups using a permutation test. So again, we're going to be doing something similar as the before one, where we check if the two means of the GPA are equal, but instead we do a different method where we use permutation test. So this code is a little bit harder to know, but you don't really need to remember this. Remember that you will just need to copy paste from your lecture notes. So the main thing you have to do is just know which function to copy and how to modify it. So again here, so the group indicator will be the admit, so whether you admit or don't admit. And what we're trying to observe is the GPA. So first of all, we calculate the observable difference. So this is the actual difference between the data between our so we calculate the mean of the observed data of the data where there is where the people got admitted. So we calculate the mean of the GPA of the people who got admitted, and we subtract by the GPA of the people who did not, the mean of the GPA of the people who did not get admitted. So this is the standard finding the observable difference. Then the next part is the actual permutation function, which remember that we're trying to find the test based on permutation. So what the first thing does is just creates a function named perm.function, and the first line in the function, it just takes a sample of the group indicator. So it's basically going to create a vector, and it just randomizes the labels. So it'll just randomize the column of the group indicator here. It just randomizes it. So this is, remember, permutate. We're trying to permutate the data, so we just permutate the labels. And then now we calculate the mean again with the new label. So this is what this does. So it just calculates the mean of the new data set, basically. It's like a new data set where we permutate it, but it's just where the labels are shuffled. And so the same thing like the observed difference, but instead we use the new labels that we shuffled, and then it returns Z. Then we just, to get the permutation, the perm diff, we do it a lot of times so that just to make sure that the value is accurate. And when you have repeated 10,000 times, you just need to check if the mean of this is greater than the observed there. So we want to see if the average, like the, because we're gonna get a vector of a lot of doing this a lot of times, 10,000 times, and we want to see if the average we want to see like how many of them are greater than the observable difference, because this will tell us whether it'll basically tell us if the students who got admitted is higher than the average of students who did not get admitted. So it will basically test. So if the probability is very high, then like this probability will be treated as the p-value. So if it's high, that means that we fail to reject. But if it's very low, then we will reject the null hypothesis. So this is basically just gets the p-value essentially. And I think there's different forms, whether it's like, I think there's one with absolute value less than observable diff, and like one that's less than. Just remember what the alternative hypothesis is used here. So I think in the lecture notes there should be that. So in this case, because we're higher, then we want to be greater than. And for the last part D, we're trying to compare the answers of B and C and comment on the applicability of the permutation test for this type of data. So you can see in B, let's run the C. In B, we get the value of 0.0001669, and in C, we get this. So this is like 0.0001. So you can see that they're approximately similar, like they're very close. So because they're very close, that means that we can use the permutation test. So if we got different values, then we would just say that the values are very different. So we can't really use permutation tests in this type of data. And also, um, yeah, so by different, you just need to have a feeling like if this and this are similar, because I think if the question intended to be different, then it'll be very different. It wouldn't be that close to the number, so it's kind of obvious if your value is different. So don't really think about like what is the meaning of different, like how different should it be. Just see it later on in your test and just make like a reasonable guess whether it's different or not, just by comparing the value. So that's for question 2. So that just basically teaches us how to use the t-test and the variance test and the permutation test. So let's move on to question 3. So question 3, let's see the full question again. So question 3, it tells us to do the data based on the admissions data, and we want to get the probability of getting admitted. So
Yeah, I think I'll go through. Oh no, you got it.
what? I think I'm doing this one right.
Okay, got it.
So for question 3, um, the first part just talks about fitting a logistic regression model on the entire data with admit as the response variable y, and GRE and rank as the independent variable x. And we interpret both of the slope coefficients or the exponential coefficients of the coefficients. So it just says to first fit, that's the first part of the question, and the second part is to interpret the slope of the coefficients. So if you want to fit the model, so the first part is just to this is basically one line. So we just named the model here, logistics M. So generally M is just for model, and GLM will just give us the logistic model, and we just put in what they tell us to do. So it tells us to admit as the y variable with respect to the two x variables, which is the GRE and the rank, and the data is just the admissions, and then family of binomial. It just tells us that the class of the admit is either 1 or 0. And then afterwards, we just call a summary of the model, what the model predicted. So we get a lot of data, but it tells us to interpret the slope coefficients. So you can see that the intercept is the first value here. So the coefficient is here for the intercept. And there's two coefficients here for the GRE and the rank. So if you want to interpret the first one, which is the GRE, it just tells us the GRE score. So if this increases by 1 unit, then the log's odds ratio of getting admitted decreases by 0. By this amount, assuming that they give for any given rank of the undergraduate university. So it means like if we keep this constant and if we increase this by 1, then the log odds ratio will increase by this much. So this is like a template answer you should remember. If I increase this by 1, then the log's odds ratio increase by this amount. But we keep the others constant basically. And same case for rank, you can interpret it in the same way, but because it's negative, then that means that if we increase this by 1, then the log odds ratio, sorry, not log odds ratio, the log odds of getting admitted would be decreasing by this amount. So it decreases by 0.55. So again, remember that you have to keep the other one constant. So that is for interpreting the coefficients. Then the second part, B, says to carry out a four-fold cross-validation to compare the average AUC score of these following two models. So it tells us model 1 we have to do with GRE, the second one is about GPA. So it says to do a four-fold cross-validation. So first of all, we need the library, the PROC. Then this part is just to divide it into 4 different groups because we're doing a four-fold cross-validation. So we divide into 4 groups randomly. So yeah, so that's the randomly given the groups. And then we'll have vectors here. This is just to put in the vectors for later. So we just store some vector. Like this is a temporary vector holder. And because we're doing four-fold, we have to do it 4 times also. And what the first thing does is it creates the model 1 based on GRE and rank. So it's the same thing like before where we create the model. But in this case, because we're doing a cross-validation, we want to, if we divide our data set into 4, so for example, if we have a data set and we divide into 4 parts of the data is like this, and we divide into 4 parts, then if we are training on these 3, we want to test on the last one basically. So we're going to do it 4 times, so the test will be on each data point, like the first box, second box, third box, and fourth box, but we train with the remaining 3 boxes. So if you see from the code that I trained the model, so I trained the GLM1 based on the data, but not including the one that we're testing. So if we're testing I, like which is the fourth, or like just any number, 1, 2, or 3, or 4, it means that we're not going to be training it on that data set too. So we're training everything besides that. So we train both models, and then afterwards we want to predict the one that we left aside. So these are the 2 predictions. So again, we predict based on the first model, and this is the second model, and we use the data set where the group indicator is equal to that I. And then the next part is just creating the ROC curves based on the actual data and predictions and for both the curves, so both the models. And in the end, we just want to calculate the area under the curve. And because we're doing this for each vector, we're doing it 4 times basically, because for the 4-fold, then we have 4 values here. So we need to take an average of the area under the curve. And once you do that, you will get this value here. I think I'm missing one. Yeah, I think I need to add this first. Also, so what's that put here? So we calculated area under the curve, the average area under curve for the first model. So we also need to do it for the second model. So here's this. So for the second model, it's 0.668. The first model is 0.67. So that means that, oh, I don't know. Okay, I think maybe mine's, I don't know if it's random, but my one's a little bit different. So I
It's because
guess,
of setting seed. Because we
oh,
take a
okay.
sample, and
Oh yeah,
so
that's true.
um, yeah, if you set a seed, basically you'll get consistent results. Because if you run it every time, the sample's different.
Yeah, okay, that's true. So just make sure that later what your conclusion is based on is gonna be based on what the values you get. So yeah, so like he said, you should probably set a seed, and then based on the seed, like based on the values, you just need to make a conclusion. So in this case, okay, so in this case, the first one is higher than the second. So what the statement you can say is the average AUC value is slightly higher for model 1, and which suggests that it has slightly higher predictive power. So basically what AUC just tells us is how good the model is, the predictive power of the model. So we have a higher AUC, higher predictive power. So that's all you just have to mention. Okay, yeah, that's it. That's it for question 3.
All right. Yeah, for question 4, oh, sorry, let me share my entire screen. Yeah, so basically here we want to fit a linear regression model that models between the average GPA as a function of the admit and GRE. And we also want to interpret all the coefficients. So we have beta 1, beta 2, and beta 3 for our regression model. So fitting this regression model, we want to model the GPA as admit and GRE. So that's exactly what we're doing with the LM function. So running the GPA as a function of the admit plus the GRE, very similar to how we did it in the logistic regression example. and setting our data as our data set from above, we get our linear regression model. And we run summary to get all the coefficients. And when we run this, we get some important values. So things to look out for here are these estimate values. So these would be your beta 1, beta 2, beta 3. This first one will be your intercept value, so your constant value. The second one here is as admit goes up by 1, our GPA goes up by 0.09. GRE, as GRE goes up by 1, our GPA goes up by 0.001. And interpreting these values is like so. So your average GPA for a student who did not get admitted and has a GRE score of 0 is 2.65. So 2.65 is your average GPA for people who have not gotten admitted and have a GRE score of 0. And your average difference in GPA is 0.09 between students who got in versus who didn't get in. So when admit is 0, then we wouldn't add this 0.09. But if admit is 1, then we'd add this 0.09. So think of it as like 2.65 plus 0.09 times admit plus 0.001 times GRE. This is basically what we're seeing here. And so the GRE score increases by 1 unit. The average GPA also increases by 0.001. Moving on to the interpretation of the p-value. So we see that the p-value, so the probability of the test statistic, here it is 0.01, and that is less than 0.05. So I think that was what it was. Yeah. So here we interpret as so there's a 1.81 chance of the slope being 0.09 or something more extreme when our null hypothesis of the slope of admit is equal to 0. And then for 4C, we want to interpret the coefficients of determination. And basically for this, what we're looking at is the variation. So here we look at the multiple r squared, and this is basically your basically this value here, r squared value. And from this, we can say that around 16% of the variation in GPA can be explained by this model. So that's actually quite a poor score. But yeah, that's how you basically determine it. Be careful of this adjusted r squared value on the right. You can interpret this, but it's slightly different. So make sure to take this r squared value, the multiple r squared. And then the last part is constructing a bootstrap confidence interval for the average difference in GPA between students who got admitted versus students who did not get admitted. So we're bootstrapping here to create a wider sample. And based on this confidence interval, do you think GPA is related to the admission status? So one thing to look out here is this final question: do you think GPA is related to admission status? This interpretation is based on this confidence interval here. So we'll see when we get to the solution for this. But basically, we want to create our boot function. This is in the week 7, I believe, for bootstrapping. So you can find that there. And basically what we're doing is we're taking a bunch of samples and setting replacement equals to true. And we're taking our linear regression model and getting the beta 2 coefficient. So the coef would take out the coefficients part, so these estimates, and then we take the second index for that coefficient, and we return it as our output for our boot function. And we want to replicate this 1,000 times for this boot function, and that'd basically be bootstrapping um, our linear regression model for this for this coefficient. And then when we do the quantile for it, for the 5% confidence interval, so 0.025 and 0.975, we get these values. And the one thing to look out for here is whether zero is included. So if zero is not included, then we see that the emission status is significantly correlated with the GPA because we're 95% sure that it's that that the slope is between 0.01 and 0.168. So if it did contain zero, then we can't say it's correlated with the GPA since there could be no correlation, like zero. Like any increase in admission status doesn't affect GPA. So if there's that potential, if there is that zero, then we would not say this. But since there's no zero, then we say that it's significantly correlated. So just to kind of recap here, we fit the linear regression model for GPA using admit and GRE. We looked at the summary. We looked at these three coefficients here, as well as the p-value for admit. We interpreted them as increases in units versus how it would affect the GPA, as well as the percentage chance of the slope being this value here or more extreme. And then we took the R-squared value to see how well this model fit our data. And then we did a bootstrap confidence interval using the second coefficient here, the admit coefficient, and replicated many times to get the confidence intervals. And I'll give it back to Valdy for the last question.
Okay, I'll explain the last question. So the last question, the first part of the last question asks us to use the apply data, and suppose you want to predict the classes of apply using other three variables. So there's three x variables we want to use to predict: paired, public, and GPA. So it says use of 60-40 train and test split to compute the following tasks. First, build a decision tree model using a linear/non-linear function of these things. Based on the train data, plot the tree, and calculate an overall accuracy for the test data. So if you want to go over the code, so the first part is just loading in the CSV. Then the next part is to add, no, this is the whole function here. So it adds a new column because mutate creates a new column, and the column name is group indicator, and the value is basically either train or test, and the size of this column is the rows, number of rows, the data, and basically this probability just tells us that 0.6 of the times in the sample, because this was one whole function, so 0.6 times of the sample for train will be 0.6% or 60% of the data will have a train label, and 40% will be from test. It's because they asked us to use a 60-40 train test split. So if we wanted to do a 70-30, we just change it to 0.7 and 0.3. And just remember to replace is true. Then afterwards, we want to get the two types of data sets. So we just filter based on train and test. So we have a test data set and a train data set here. So now that's just the setup because they tell us to do a 60-40 train and test split. Then for part A, they asked us to build a decision tree model. So based on these three factors. So we just have to use the rpart library, and this essentially just creates a model, decision tree. And because apply right now is numbers, I think 0, 1, and 2. We can just head it here. Let's see. if I add the data, then yeah, so admit, no, I need to run this one again. Then if I do this, apply is 0, 1, and 2. So basically these are treated as numbers. So they're not treated as separate categories. And for decision tree, in this case, we want it to be categories. So you just put as factor. So make sure that the label 1 and 0 and 2 are all treated as different categories. Then we want you just use a squiggly line to this is the y value, and this is like the three things, the three factors that you're basing it off on, and it tells us to use it here based on the three variables, paired, public, and GPA. And remember that to use the train model to train the data, don't switch it up, don't use the entire data, but always use the train. And this is just to add it to be a classification. And then we have already trained the model by doing this. Then if you want to plot the model, I think, did it ask? I didn't really ask, I think, but oh yeah, no, it says plot the tree. So to plot the tree, you have to use this, just use this code, fancy r part plot, and just put the model inside, and it'll create the decision tree here. Then afterwards, it says the next step is to get the accuracy of the test data. So in order for us to get the accuracy, first we need to predict the value. So how do you predict? We use the test data, and we create a new column, and we call it apply pred. So that's basically just prediction of apply column, and we predict by calling the model and the data tab, the data, which is the test data, and this is just class to talk about it as a classification. And then once we have this, that means that we'll have a column. Let's just head D dot tab. It will create a column of data for the predictions that we are making for apply. So like based on these three values, we are predicting if whether it will be 0, 1, or 2. So that's what basically we did. And afterwards, we want to make the confusion matrix. So we just do this command where we put table, you put the actual value, and this is the prediction values. And we will get something like this. So basically the top represents if the actual value is 0, and this is the prediction is 0. So if we are accurate, like if we predict correctly, we'll be in this one here. So it'll be 64. Then this one will be the incorrect ones where we predicted it as 1, but it's actually 0. So this is basically just tells us how much of them are we predicting correctly and how much of them are we predicting wrong. So the wrong ones are the ones in the not diagonal. So what we want to do is to get the accuracy is we sum the diagonal. So if we sum the diagonal of the conmat, so this one just gets the diagonal. It sums all the accurate ones because these are the ones that we accurately predicted. And if we want to sum the whole, and then we just sum it by the whole the confusion matrix to get the overall accuracy. So this is like how much we predicted correctly divided by the total amount of predictions we made, basically. Then we'll get accuracy to be this value. So that's how you do the decision tree and getting the accuracy. But this time it says here basically to build a random forest model using the same function you used in part A based on the training data and calculate overall accuracy. So it's basically the same thing, but instead of using a decision tree, we use a random forest. So we have to use the library of the random forest this time because we're dealing with random forest. And this is the random forest model we're naming, it doesn't matter. Then just call the random forest function and do the same thing, where we put as factor because we wanted to make it in terms of categories. And these are the three variables we are basing it off. And this is the train again. Remember to make sure you use train and not test or the whole data set. And here just tells us the number of trees we want to make. And since it doesn't say, it doesn't mention anywhere, you can just put 500 or the default value in the Shams code and just put importance as true. Then afterwards, we've already created the model, the random forest model, so we just want to we want to predict again. So to predict, we use the test data set and we create a new column. We call it apply prediction, and we predict based by using the predict function. We put in the model you're using to predict and the test data set. So this will give us a new column with all the predictions. You can see here if you want to add e.test. So here, the apply pred. So this is the new prediction. And then we have to just calculate accuracy. So we just do the same thing again where we make a table where the confusion matrix table, which is based on the correct values of apply, and this is the predictions. And if you want to see it, here's the con matrix. And afterwards, you just do the same thing to calculate accuracy, where you sum the diagonals and you sum all the predictions. Then you can see that our accuracy is this compared to this. So you can see that the random forest is slightly better, which is good because generally random forests are better, and this will be explained by part C. But then for part A and part B, this will be a typical question, and generally the steps are four steps. First thing is to split the data into train and test. The second part is to train the model. If it's a decision tree, we use the R part. If not, we use decision tree. For the decision tree, we use the random forest. Sorry, the random forest, we use random forest, and decision tree, we use R part. And then after we have trained the model, we just predict into the test data set. And afterwards, the last step is the fourth step is to create the confusion matrix and calculating the accuracy. So that's just something you have to remember. Then the final question is why random forest models are expected to outperform decision tree models. So we have to explain briefly. So I think this is in your lecture notes, so you can just remember. You don't have to. Like, I guess it's good to remember, but if you can find it, then you can copy it. So it just says decision tree only fits one tree with the full model, whereas random forest fits a number of decision trees with smaller models, and in the end averages all the predictions. Hence, random forest is expected to give robust predictions and expect to outperform decision tree models. So basically, in short, it's like the decision tree only makes one tree, while as the random forest makes a lot of trees that are a little bit different from each other, and they use the different trees and they average the different trees. So because of this, it becomes a lot better than just having one tree. So that's why the random forest is better than just having a decision tree. I think that's it for question 5, which is the final question.
Yeah, and I think that ends the review seminar. So yeah, thank you all for coming out here. We'll be posting the R code on the AMACSS community Discord. So if you haven't joined that yet, then it's up on the Quarkus announcement that Shams sent. We'll be posting it there, and we'll also be posting this recording up on our YouTube channel. So yeah, hopefully this helped out. We're very open to feedback, so if you have any, just shoot one of us a message. And yeah, good luck with your exams, everyone.
Good luck.